Section 5.1 introduces us to the topic of this unit, which is probability. A lot of statistics problems focus around the concept of randomness, which is the idea that for any particular event, we don't know what will happen, but in a lot of cases, we know what can happen and how likely those events are. And that's the basic idea for probability. When we have chance behavior that's unpredictable in the short run, but in the long run, when we look at it, it has a predictable pattern. A more specific definition for probability is a number between 0 and 1 that describes the proportion of times that some outcome would occur in a large number of trials. When we say probabilities between 0 and 1, we're including those numbers because an event with a probability of 0 is impossible to occur. Conversely, an event with a probability of 1 is certain to occur or guaranteed to occur. And as an example, an outcome that happens half the time over a long series has a probability of 0.5. Again, these are long-term estimates. So if we were to flip a coin 4 times, we might get heads every time. But if we were to flip it 4,000 times, we would see that proportion of heads get closer and closer to 0.5. This is called the law of large numbers. As the number of trials increases, the proportion of times that a specific outcome occurs approaches its true probability. So according to the Book of Odds, the probability that a randomly selected US adult eats breakfast is 0.61. First, we want to explain what this probability means. And it means that if we were to take a very large sample, random sample of US adults, about 61% of them will be people who usually eat breakfast. In part B, it asks, if we randomly select 100 US adults, will exactly 61 of them usually eat breakfast? Probably not, because just like everything in life, things vary. All right, so the 61 is about the long-term, really infinite number of trials. If we take a sample that's 100 people, maybe instead of 61, it's 60 or 63. All right, as the number of trials increases, that proportion should get closer to 0.61. To explore the concept of probability a little more deeply, we have this example here about a breakfast company that's offering NASCAR collectible cards inside their boxes of cereal. There are 5 cards for 5 different drivers, and the company claims that each of these 5 cards is equally likely to appear in any box of cereal. Down here, it notes that we have a NASCAR fan who wants to buy boxes of cereal until she gets all 5 drivers' cards, and it ends up taking her 23 boxes to get that full set. Right? Does the fact that it took so many provide evidence that these 5 cards are not equally likely to be found in each box? Are certain cards rarer than others? And to figure this out, we're going to perform a simulation, which we did a bit in Chapter 4. And that's going to help us estimate the true probability, the long-term probability, that it will take 23 or more boxes to get that full 5 NASCAR set of cards. So when we conduct a simulation, we're simulating a real-world process with something that just simplifies it. So in this case, we're going to use a random number generator. And it told us that there are 5 cards in these boxes, and each one is equally likely to occur. So we'll just say the number 1 will represent that first driver, Kyle Busch. The number 2 will represent the next driver, Haley Deegan, etc., until we get to 5. And then we're going to use our random number generator to randomly give us a number between 1 and 5. That's simulating buying a box of cereal, opening up, and seeing which card is inside. All right, and we're just going to keep doing that, keep getting a random number between 1 and 5 until we collect all 5 of these drivers. And we want to count how many boxes did it take for that to occur. So now when we're doing a simulation, we would repeat that process over and over again. It's done it for us here. We have a dot plot showing 20 trials of the simulation. It's asking to start, what does this dot above the 20 represent? So that represents a single simulation of collecting 5 cards. So they got a whole bunch of random numbers between 1 and 5, all right? And it took 20 numbers to finally get that last card. So now the simulation was done 50 times. You'll see 50 dots in this dot plot, and each of those dots represent how long it took to get all 5 cards in a trial. Now we want to estimate what's the probability that it would take 23 or more to get a full set of cards. 23 is not actually even in our simulation here. So of the 50 trials that we ran, represented by those dots in the dot plot, 0 of them took 23 or more boxes to get the full set. So the probability of this happening is 0% according to our simulation. Now, does this provide evidence that suggests that the 5 drivers' cards are not equally likely? It wants us to explain our reasoning. So the fact that we didn't see a 23, okay, which is what the person in this problem got, that's giving us evidence that something about our setup here is actually incorrect. This simulation is simulating how long it will take, given the assumption that these cards are equally likely to be found in each box. Now, if that's incorrect, then this simulation is no longer relevant. And that's the explanation that we go with as to why we didn't see the result that she saw. The fact that it took her 23 boxes is not because she was just really unlucky. It's because the actual, the guidelines for a simulation, the fact that it's telling us all these cards are equally likely to be found, is not actually true. There might be one of those cards that's really rare. Maybe instead of 20%, it's 5%. And that's why it takes so long to get all 5 cards.